Hello, everybody. Welcome to the MIT Category Seminar. Today we have Robert Paré, who's going to talk about retrocells, so in particular about double categories and cofunctors and some of the links between the two. I just asked the audience, if you want to ask questions, feel free to raise your hand on Zoom or write in the chat, or of course also write in Zolip or on YouTube. Please, Robert, go ahead. Welcome.
Okay, thank you very much. So this is a talk that I gave a similar talk in Edinburgh last year, and so it's a little bit improved or augmented from that. Okay, so I apologize for people who were there last year and who actually remember what I talked about. Then you might get a sense of déjà vu. However, I always find that it's good to hear talks several times, maybe with a different flavor to it, you know, because I don't usually understand everything in the talk, and often at conferences I say, oh, look, this is interesting, I'm going to look at this, but then when I get home, you know, everything sort of kicks in and I forget about it, okay? In fact, I had forgotten about this until I was speaking to David about this, and so I think that this is justified. Okay, so, whoops, there. Let's just start as a motivation here, looking at the bicategory of bimodules. So the objects are rings with one but not necessarily commutative, and the one cells are bimodules, M. One cell from R to S is a left S, right R bimodule, and then the two cells are linear maps. And composition is given by tensor product, and this bicategory is biclosed. That means that the tensor has a right adjoint. The tensor in each variable has a right adjoint. And so here, maps from n tensor M into P are in bijection with maps from M into, this is a HOM here, and it's also in bijection with maps from P into from N into P over M. Okay, so P over M is the R HOM from M to P, and N under P is the T HOM. Okay, so this notation I took from Lambeck's book Rings and Modules, 1966. So you have multiplication, and then the right adjoint is division in some sense. So it's division on the left, division on the right. Okay, so some people use lollipop for this. Okay, well, so many bicategories are biclosed, and I'm going to explain how they are in a minute. So BIM bimodules I already talked about. But prof, the bicategory of categories with profunctors and natural transformations is, you can generalize that to V prof, provided V has colimits preserved by tensor in each variable to make it into a bicategory, first of all. And then if V is biclosed and has limits, then you get you get these internal HOMs. Span A. So, and I'll just in case you don't know what span A is, I'll explain that in a while as well. So span A is, if A has pullbacks, you need that to make it into a bicategory, and then if it's locally Cartesian closed, span A will be biclosed. And mat V, so this is matrices whose entries are in a monoidal category V. So the objects are sets, but a morphism from a set A to a set B is an A by B matrix of V objects, okay? And if you have coproducts preserved by the tensor, then you can define matrix multiplication. And if it's biclosed and it has products, then mat V is also biclosed bicategory. Okay, so let's just look at how these various bicategories are biclosed. So I've already discussed what the internal HOMs are in BIM. And for prof, if you have a profunctor from A to C and a profunctor from B to C, then Q under P at AB is given by the set of natural transformations from QB blank, so there's a functor in C, into PA blank. Okay, so that's what the internal HOM, at least the left one, is in prof. vprof is similar. You have to do some sort of generalizing things to V, you know, which I'm not going to go into here. Okay. Now span is also biclosed. So span is a span of sets. Okay, so a span from A to B is a set S with projections to A and to C. Okay, well, I said B. So a span from A to C is a set together with these two projections. And so if you have a span from A to C, S, and a span from B to C, then the internal HOM is given by the following set. It's a set of triples. Okay, so the first is an element of A, the second is an element of B, and the third is a family of functions from TBC into SAC, okay, for all C, with the obvious projections. So you can work this out easily enough. Now, span set can be generalized in a couple of directions. And let me just give sort of some alternate ways of looking at the closeness. So if A has pullback, whoops, sorry, what did I do there? Yes, suppose A has pullbacks and is locally Cartesian closed. So then for spans R and T, so I'm just, this is sort of internalizing the definition that I had on the previous slide, okay? So, but I'm giving a different way of looking at it. So if you have a span from A to B, that's the same thing as an object over A cross B, R over A cross B. And then to compose them, you pull back along the T0, that's the projection from T to B. Okay, so A cross T0, you pull back, and then you compose here with A cross T1, tau 1. Okay, so that now you have something P over A cross C, and that's the composite. So composing with T then can be written like this. So you have the slice category A over A cross B, you pull back, and you get something over A cross T, and then you compose with tau 1, and you get something over A cross C. Now, this sigma here, which is just composition, always has a right adjoint, namely pulling back. This guy here, A cross tau 0 star, that's pulling back, will have a right adjoint provided A is locally Cartesian closed. Okay, so that's a proof that span A is biclosed, at least left. This is the left one. The right one is completely dual. Okay, so MAT, so I just giving you this. So this is a different way, again, of looking at things. You can generalize spans to MAT. Okay, so an object in MAT is a set. And a morphism in one cell in MAT is a matrix. So morphism from A to C is a matrix VAC. So it's an A cross C matrix of objects in this monoidal category V. Okay, so you look at, and a morphism is a matrix of morphisms in V. So now you look at the composition, which is matrix multiplication, and you look at what are morphisms from W tensor X into V. Okay, so W tensor X here is given by this formula here, which is matrix multiplication. And then you're getting a morphism here. So it's a family of maps going from the sum into VAC, indexed by A and C. But of course, a map out of a sum is just a family of maps indexed by B. So what you get then is that these are in bijection then with families from W sub BC tensor XAB into VAC indexed by A, B, and C. And so now you can flip this W over and use the internal hum in V. So I'm assuming that V is itself biclosed. So this is the internal hum in V. Now I have a family of maps, but still indexed by A, B, and C. But I want something indexed just by A and B. And so I take the product over C of all of these guys. So a map from here into there is the same thing now as a family by indexed by A and B. And now this is a family, it's a matrix of morphisms from XAB into this product here. So this gives you then the internal hum this way. So these are sort of three different ways of looking at the internal hum there. Now, so here, this is a scandal. It's a scandal for people who believe in double categories. Of course, for people who don't believe in double categories, then maybe it's a windfall. Okay, is that all the bicategories that I've mentioned there are the vertical part of naturally occurring double categories. So BIM is the vertical structure in a double category called ring. Okay, and I'll explain in the next slides what these are. And prof is in the double category that's called cat, and vcat is for vprof, and then there's a double category of spans, and something I call vset, which comes from matrices. Okay, but the problem is now is that these internal hums are not double functors. They don't work well at all with double cells. So let me just mention what double categories are for people who don't know it. I am not going to give a definition. I give a sort of general idea and then some examples. So a double category is a category with two sorts of morphisms. Of course, this doesn't make any sense because, of course, a category is determined by its morphisms. So if you have two sets of morphisms, then you have two categories. So a more precise way is that a double category is two categories, but with one sort of object, if you like. So, but still, this is the way I think about it. It's a category with two kinds of morphisms. So we have examples of this, and the first example is ring. Okay, here there are two kinds of morphisms between rings that you can consider. You can consider homomorphisms. So that's an F here from R to S, or you can consider bimodules. And these are not really unrelated. So what you have then is the double category of rings has rings as objects, and as horizontal arrows, homomorphism, as vertical arrows, it has bimodules. And then it has these double cells that tie the horizontal and the vertical together. And these guys here are, in this particular case, sort of linear maps. Okay, so it's a function from m to n that preserves addition, and it preserves multiplication by scalar in the only way that it can once you factor in the f and the f prime. Or another way of putting it is you take this bimodule here, this s prime s bimodule, and then you move it back to an s to an r prime r bimodule by restriction of scalars. Okay, so this is the double category of rings. Okay, so good. The double category cat, and I'm thinking of this as being cat itself in the double world. Okay, so an object is a small category, A, and a horizontal arrow is a functor, and a vertical arrow is a profunctor. So here I give you my convention here. A profunctor from A to C is a functor from A opposite cross C into set. So not everybody takes this convention. I probably 30% of people who talk about profunctors use this. and 70% use the opposite, so that a profunctor from A to C would be something from C opposite cross A into Z. I sort of change back and forth every couple of years, but I think this is the correct one now. Anyways, so this is what a profunctor is. And I should just mention, while we're talking about conventions here, that for me, the horizontal is the strict direction, and the vertical is the weak direction. So this is contrary to many people as well, okay? But just the decorated ones are the fancier ones, okay? That's so, and then I just mentioned V set here. So V set, the vertical bicategory here is mat V. So an object is a set and a horizontal arrow is a function. Okay, so it is sort of a little bit like the category of sets, but then we have these funny sort of fancy relations, if you like. Well, they're matrices taken from V. Okay, so it's an A cross C matrix, and a morphism, a double cell is it's a matrix of morphisms in V, phi A C, going from VAC into W, but now you pull it back like this. Okay, so into W F of A G of C. Okay, so this is this bicategory here, and then finally the last example is spans. So a span, as I said before, a span from A to C is an object in A together with two projections. So here this is a morphism, a vertical morphism from A to C. We have T, vertical morphism from B to D. The horizontal morphisms are just morphisms in A. And the double cell is a morphism of spans like this. So it's an H making these two parallelograms here commute. So I think that I've given you 4 or 5 examples of double categories. You should have an idea what they're like. Now, let me talk about left hams. Okay, there are left hams and right hams. I'll just look at left hams. You know, right hams are of course dual. Okay, and so this. Whoops, sorry. No. Yes, this is I touch the mouse and it does that. So A has left hams if vertical composition, if for every Y, vertical composition by Y has a right adjoint. Okay, Y. So this is Y times blank, or a map, if you like, cells going from Y times X into Z are in bijection with cells going from X into Y under Z. But all of this is going on merely in the vertical double category. So it's not really in the vertical bicategory. Okay, so it's not really a double category construct. It's a bicategory construct. Okay, and we would like to sort of improve this somewhat. So these were introduced by Mike Schulman in this paper, Framed Bicategories in TAC, and used extensively by Roald de Coudenberg, studying con extensions in double categories. Okay, so this is what left hams are. Now let's just see what the problem is. So the problem has to do with the boundaries of the cells. Okay, so yes, so Y under Z is. So this is covariant in Z and it's contravariant in Y invert. Okay, so invert of A, okay, in the vertical thing. And so how that works, I think everybody knows, but let me just mention it. I have an evaluation cell. So the two cells in vert A are these globular cells. So they're cells. So cells in a double category are squares. And if the top and the bottom are identities, then I call them globular cells. And this is what gives me the double category associated to A. And so you take your cells here, Z, gamma going from Z to Z prime, and beta going from Y prime to Y in the backward direction. And you take your evaluation cell, that's what mediates here this bijection, and you can paste this gamma on the right, put the beta here and then fill in an identity there. And now you have something from y prime composed with this guy into z prime, so you can flip this y prime over and you get something from y under z to y prime under z. So all of this is going on in the bicategory vert. Okay, so I would like this to be a double category thing, so I'm going to try and replace gamma and beta by general cells in the double category. So what happens if we take beta and gamma to be cells, then we have still our evaluation here, and we have gamma. Now it has an A as its vertical domain and a C prime as its vertical codomain. And we put a beta here. Now we have nothing to stick in here. Okay, but even if we could, so there are conditions, I'm going to talk about conjoints in a few slides, and if B had a conjoint, I could fill this in, but even if I filled it in, you see the domain here is C prime. It's not an identity, so this is not going on in vert A. Okay, it's in A, but it's not in vert A. And just trying to sort of give a definition of what kind of universal property that you get doesn't work. Okay, so I mean, I tried all sorts of things and it didn't work. Okay, so let me just contrast here the universal property. Okay, so the universal property, this is just in vert A. Okay, just says, I mean, I'm just rephrasing this in terms of universal cells, right? Given an alpha from y times x into z, then I get a unique beta from x into y under z with the property indicated here that if I compose epsilon with beta and an identity here, I get alpha. Okay, so now I'd like to try and make this alpha here into a double cell and the beta into a double cell. And so you actually need to keep this identity because the internal HOMs have to do with maps that have common codomain, okay? But you can change the top. So you can stick in an F here, and this makes it a bit more universal, okay? So now I'm just, you can write down the same definition for every alpha, but now there's an F there exists a beta with the F, and if you compose this beta and the identity with epsilon, you get alpha back. Okay, so this is what I'm going to call the strong universal property. So a double category now I want to say, so I'm changing the definition a bit, is vertically biclosed if it has left and right HOMs, the under and over satisfying the strong universal properties like this. Okay, so now let me, every talk I give on double categories, I talk about companions and conjoints because I think that's a really neat idea. In a double category, there's a way of saying when a horizontal arrow and a vertical arrow are the same or are isomorphic. Okay, so the definition is being a companion. So a vertical arrow is a companion, so V is a companion of a horizontal arrow F if there are binding cells. So cells like this, because you have F and V and you have identities there. So, I mean, if you imagine that you could compose, which you can't, but if you could compose this identity with V and this identity with F, then you're getting something from F into V. And the same thing on this side here. So V is a companion of F if you have these alpha and beta here, and if you compose them horizontally, you get a vertical identity. And if you compose them vertically, you get a horizontal identity. So this is the definition of companion. And they don't always exist, but when they do exist, they're unique up to globular isomorphism. So we can make a choice of them usually, the way we usually do. And then we don't use letters for the binding cells, we just use corner brackets. That makes the things somewhat simpler, okay? One of the things is that the vertical identity is companion to the horizontal identity, which you think, I mean, if they're going to be the same, that certainly should be true. And also companions compose in that way, that there exists globular isomorphism between the composite of the companions and the companion of the composite. Now, given, so this is sort of important here, given just a general cell here, phi, with this boundary, you can flip the F up and the G down. Okay, so you can put F star here and G star there. And here you put in these binding cells. And what you get then is a globular cell from G star composed with V into W composed with F. And this is, in fact, is a bijection, because now you can just stick here binding cells here, and it goes back. Okay, so you have this bijection between arbitrary cells and globular cells. Now, there's a dual notion to companion which is called conjoint. It looks exactly the same. Well, it looks dual. Okay, so now you have F upper star is going in the reverse direction. So you have F going from A to B, the F upper star goes from B to A, but vertically as well. And you have these conjunctions, psi and chi. If you compose them horizontally, you get a vertical identity. And if you compose them vertically, you get a horizontal identity. So what you're thinking is that F upper star is an adjoint to F on some side or other, even though they're not the same kind of morphism. So we actually see this from time to time. Yes, in various contexts, that you have things that are a little bit different, but they're adjoint. Okay, so this is, for example, lax morphisms between monoidal categories can have left adjoints, which will be oplax. Okay, so they're not the same kind of thing. Okay, but so this is conjoint. I'm just going to mention this. And so in my examples, every homomorphism has a conjoint and a conjunction. F lower star, the companion. Right. Let me just say that correctly. Every homomorphism has a companion and a conjoint. The companion is S, but considered as an SR bimodule, where you use F to get the R structure. And F upper star is also S, but considered as an SR bimodule. In CAT, for profunctors, you have you can plug into the Hom functors the F. If you plug it in the first variable, you get the companion, and if you plug it in the second variable, you get the conjoint. And in span, the companion for F is F with the left leg an identity, whereas the conjoint is the left leg is F and the right leg is the identity. Okay, and in V set, these are matrices, then it's given by a matrix of zeros and ones, or actually zeros and i's. Zero is the initial object here, zeros and i's with this delta thing being the Kronecker delta. Okay, so
there may be some questions.
yes.
Maybe they've been addressed. So
No.
I don't know
Okay.
if
Yes.
if Brian Pinsky and Paul Taylor want to ask or.
Yeah, I mean, I was just asking when you first had this dot notation. So you're assuming the vertical category has like some kind of product, and that's how you're defining the exponentials here, right?
Yes.
Okay.
Okay, so you can compose the arrows and the cells horizontally and vertically as well.
Mm-hmm.
Okay, yes. So it's a composition that has right adjoint, which is often like a tensor product. Okay.
Well, this is a right adjoint of just the. You can compose the cells, but I'm just like this dot notation looks like you're just composing the vertical morphisms, right?
Yes, you can compose vertical morphisms, and you can compose the cells. Okay. So the composition of the vertical morphisms in BIM or in what I call cat, no, in ring is just tensor product of bimodules. So you can compose those, but you can also compose the cells. Okay, but I didn't go into that. But
Okay. Yeah, it makes sense that one should be able to do this.
okay, yes. So
Does
Paul.
Paul Taylor
I
have
think
a...
you answered my question. I was asking you to relate your abstract definitions to the leading examples. I think you did.
Ah, okay, good. So let's.
there's also a question from Jarl. I hope I'm pronouncing your name right.
Yeah, that's the right name. I'm just, so on the previous slide.
Yes.
Go back. This F lower star and the F upper star in the bicategory prof, they're adjoints. I wonder if this follows from this two double categorical description.
Well, it is true that in the double category, if a horizontal arrow has a companion and a conjoint, then they're going to be adjoint. I forget which side to each other in the bicategory. But of course, in the case of prof, this is something that's been known for a long time that they're adjoint. Okay, and so. But it does follow. But I mean, I imagine that getting all the machinery, getting the double category working is a lot harder than just proving that they're adjoint directly. But it is true that in a double category, if you have a horizontal arrow, then which has a companion and a conjoint, then the companion and conjoint are adjoint. You have to just write it down. I forget what it is, but they are adjoint in the bicategory. Does that answer your question?
It seems it does. Thanks.
Okay, thank you.
So, in the chat they say yes. Please, we can go on.
So what strong means is simply that the internal hum now is somehow preserved by composing with companions. Okay, so here the internal hum is corresponds to the globular one. Together with this isomorphism here. So there's a comparison, and I guess the comparison would go from right to left, and it's an isomorphism. Okay, so that's what. So it's not really a great generalization having the double or the strong universal property. And in fact, if every horizontal arrow has a conjoint, then the strong and the globular one are equivalent. So this gets Mike and rolled off the hook here because they weren't using the strong one, but all of their double categories have companions and conjoints, and so it's the same definition. Okay. Now, just to simplify things, let me define the left dual. So suppose now that A is left closed, so it has these internal hums. Then I can define the left dual to simply be the internal hum V under identity on B. Okay. So I call this Isbell dual. It's not really a duality because if you do it twice, you don't get the same thing back. And it's not even what they call duals in monoidal categories. It really is a generalization of Isbell duality, which is humming into the hum functor, which is the identity profunctor. Okay, so just looking at this is simply just to simplify. Our problem is with the variable that's in the denominator there, right? So let's define left duals to be this internal hum, V under identity. And then you can show that the identity on B has left dual identity on B, and you get a comparison between the duals composed and the dual of the composite. So it looks like maybe you're getting here a lax normal functor going from A co into A. But here, if you look at this, you have a cell, you get this dual, and you don't get this. Okay, so that doesn't work. Okay, so this is the problem. So what are we going to do? we're going to define our retrocells. Okay, so here I'm halfway through the talk, and I'm just defining what the title is talking about. So I'm assuming now that A has companions. So a retrocell fitting in a square like this it's a globular cell going from W F star into G star V. Okay, so it's going this way. So if you remember, if you have an ordinary cell here, then it gives you something going in the other direction. It goes from G star V into W F star. So I'm just putting this in the reverse direction. So this is sort of a little bit of a cheap sort of thing, but let's see. I'm going to try and give you a whole bunch of reasons why it's a good concept. Okay, so first of all, if you have a two category, there's a nice double category that you can construct from it, the double category of quintets. So this was introduced by Ehresmann way back 1962 and called the double category of quintets. So the objects are the objects of A, and the horizontal arrows are the one cells of A, and the vertical arrows are also the one cells of A, and the double cells are these quintets. So it's a two cell going from KF into GH. And a retrocell then is a co-quintet. So, I mean, you might, why going, you know, from left to right here? Well, that's what Ehresmann did, but you could equally well do the other thing. And so here, the co-quintets are the retrocells. So that's, maybe that doesn't convince you too much if you're not interested in quintets. But it is sort of an annoying thing when you're working with them. So now here, suppose that you have V has a right adjoint. Okay, this is in vertical category, and W has a right adjoint. Then a retrocell in this square corresponds bijectively to an ordinary cell between the adjoints. So it's a kind of calculus of mates that you have. And similarly, if F and G have right adjoints, so F and G have right adjoints. Now in the horizontal, it's a two category now, then the retrocells are also in bijection. So you have this category of mates, so it looks pretty good. Now retrocells can be composed, so you can compose them horizontally. So you have a retrocell alpha and beta, and you get here, you put the alpha and the beta and you fit them together, and it works like that. Okay, so this is now, remember now that G star F star is isomorphic to GF star. Okay, so I should replace this here. Also, I should stick in an isomorphism here. Okay, so I didn't put it in just to simplify things a bit. Okay, and an isomorphism also on the right. Okay, so you get then, you can compose them horizontally, retrocells, and you can compose them vertically. The picture looks almost the same, except that now, before the first one was down here, and then the other one was up there. Okay, so it's just, it looks like, and these composites now give you a new double category, which I'm calling A ret. Okay, for retro. Okay, and now A ret has companions. Again, it's the same companions as the other ones, and if you do ret twice, you get A back again. So it is a kind of duality that you're getting here. Now, so duals that I mentioned before are actually functorial. So they give you a double functor going from A ret co. Co is the vertical dual. So you have to take ret and co, and then you get here a double functor. So I'm not going to go through the proof of this, but it's straightforward if you like. And the internal hum is also functorial. So if you have, but it's functorial, you need to have the alpha is a standard one. okay? But the beta is a retrocell. And they have to have the same vertical codomain, so H and H here. And then you can take you can calculate this, and I show you how you calculate this beta under alpha. You have your evaluation guy here, and you stick the alpha there, which is just alpha. And the beta now, the definition of a retrocell is that it's this globular cell that goes here. So now you compose all of these together, and what you get then is a globular cell with this Y prime here down on the right. You can flip it over, and it gives you something then from this guy here, composed with this into Z prime, and then you can flip this over here. So I mean that I don't know if you could understand that if you didn't know already, but that's what it is now. Now the origin, I mean, for me anyways, where it came from a long time ago was in this paper with Marco in 2008. We're talking about con extensions and double categories, and we needed to discuss comma categories and double categories, okay? Which comma categories come up, you know, if you want to define pointwise and stuff like that. And we introduced what were called commutative cells, which I think is maybe not the right way. Now I want to call them commuter cells. So a commuter cell is an ordinary cell, but now if you flip it up like this, so this you can always do this, as I said, and if it has an inverse, a horizontal inverse, then it's a commuter cell. So you have these cells, and you want to say that actually the square really commutes, or it has an isomorphism in it, and so that's what it is. So this is what a commuter cell is, and then the inverse now would be a retrocell, although it's not completely clear sort of how it's a retrocell with the same boundary, so it's not clear how it's inverse to alpha, but I will come to that in shortly. Yes. So just a question about whether functors preserve retrocells. A double functor will preserve retrocells, and you get a double functor from A ret into B ret. But if it's just lax, then it doesn't extend to ret. Okay, so it should properly respect the companions, as I say here. So you always have that if it's normal, a lax normal double functor preserves companions. And it also preserves composites by companions, but on the right, as I wrote there. And so I want to define F to be paranormal if it's normal, and if the other composite, which already laxity gives you this composite here, is iso. Okay. So in our paper with Doretta and Robert here, we had paranormal, but they didn't like the name. They said it makes us look ridiculous or something, and so I was outvoted, and so. But now since I'm doing this on my own, I brought it back again. I like the name paranormal, but they're paranormal operators in operator theory. Okay, so I mean it's not really. Anyways, I like it. So if X is lax paranormal, then it does extend to a not lax one now, which is paranormal, and then you can do the same thing and get it. If you take ret again, you get F back. Okay, so that's this paranormal is an important condition which comes up, you know, often. Okay. So let's look at retrocells in span now, okay? Because so I just want to see what they look like. So you have a retrocell here, phi, in this span. So you have to compose T here. This is T with F lower star. This is F lower star, and the way composition goes is you take the pullback. So T F lower star is sort of the complicated composition, and G lower star S is the easy one. You just multiply the projection here by G. So this here is G lower star S. And then a retrocell will be a morphism from P into S. So it's a morphism out of a pullback, which, you know, I don't like, okay, because, well, yes, morphisms into pullbacks are good. Morphisms out of pullbacks are, well, okay. So if just to analyze this a bit further, let's specialize A to be the category of sets. So now we're in span set, which I call it set here. Okay, so if we denote, just to analyze this, an element of T, okay, so this is the span here, T here, by an arrow from B to D, a dotted arrow, if T0 of T is B and T1 is D. Okay, so this means that T is an element of capital T and it projects down to B on one side and to D on the other. And the same thing for S. Then what a retrocell does is it will take an A here. Okay, so an element of P is an A and a T, and F of A, T maps into F of A. So it looks like this. Okay, so you have an A and then you have an F of A going into a D. And what it does is it gives you something over here, which is an S element, phi of T. And the top condition here says that the domain of this phi of T is A, and the codomain, I don't exactly know what it is, but I know that G of it is D. Okay, so this looks exactly like cofunctors, except that I don't have categories there. I have spans only. Okay, so let's put the categories in. Okay, so a category object in A is a vertical monad in span. So this is known. Okay, it's often said that category objects are monads in the bicategory of spans, which is true. But for morphisms, it doesn't work. Okay, so to get the right morphisms, you have to do this in a double category. Okay, so this is just a little bit of propaganda here. So here we have an internal functor now. So here I have a monad, and I'm calling it A0. That's so it's a monad in span. So it's a span. Okay, so it has two objects, but they're the same, and then it has a span A1, which is like this, and then a cell is a functor. Okay, and a retrocell now, and if it preserves composition and identities, then you've got an internal functor. Okay, so a retrocell, on the other hand, is going to give you an object function. So I'm getting, yes, okay, you have an object function, okay, F0 here, but now the F1 is going in the opposite direction. Okay, so I have, for each A, I have F of A, and then for each morphism from F of A into B, I can lift it. I can lift it to something, and I don't know, it doesn't make sense to say that it projects down to B, but it makes sense to say that the codomain projects down to B. And if F respects composition and identities, then this is exactly a cofunctor, but it's going in the reverse direction in the sense of Aguiar. And so I should mention that everything that I know about cofunctors, I learned mostly from the papers of Bryce Clark and reading Aguiar's thesis, which is a bit hard to read if you want to read it fast, okay, because there are lots of details and so on, but everything is there nice and precise. So this is, so we're actually getting cofunctors now. Now,
sorry, there's a
yes.
question.
Yes.
David Myers is asking, what does it mean respects composition and identities when we have a retrocell?
Okay, maybe I'll come to this later. Okay, so I'm going to say, wait, let's see if I can just say it from this here. Yes, so you have this lifting. So first of all, you take an A and you look at the identity from F0A to F0A, that should lift to the identity. So that's respecting identities. But now suppose you have a B and a B prime. So you can lift B, but now this guy here, B becomes F of AB. So now you've got another arrow. The B prime is going out of F of AB. So you can lift it. You can compose these two. This is in a category. You compose these, and it's the same thing as lifting B prime B all at once. Okay, so that's it's just right. Yes, is that okay? Good.
Does that work, David?
Yes, he gave me the thumbs up.
Oh, okay, great.
Okay, good. So let's see. I'm running short on time here, so everybody knows what a monad is. It's an object. So this is a vertical monad. Maybe you've not seen what the associativity and the unit laws look like if you write them out in terms of double categories, but there they are. Morphism of monads. Now, so there's something interesting. If you just look at morphisms of monads as you would see, let's say in Street's 1972 paper, Formal Theory of Monads, there are two different kinds of morphisms. And you wonder, which one should I take? Well, in the case of double categories, the choice is made for you, you see. So you only have one possibility is for a cell going from T to S. Okay, so you have the F going from A to B in the cell, and then these respect and multiplication and identities. Okay, so this is what a morphism of monad is. It's just translating Street's definition. And for two cells, now there's a story with two cells. If you have two cells, then if you look at Street's definition in his 1972 paper, it doesn't give you the right thing at all. And so you have to go to the 2002 paper by Lack and Street, where they introduce more complicated morphisms of monads. Okay, so they have a different two category of monads. It's the same one cells, but the two cells are a bit more general. But you can actually generalize that a little bit more and just say that it's simply a cell whose domain is T and his codomain is S like this, and F and G, and then it's compatible with these guys here. Okay, so this is what a morphism of monads is. Okay, and in span A, the monads are internal categories and the morphisms are internal functors, and the two cells here are internal natural transformations. Okay, so now the thing about vertical monads is that the two cells, the mu and the nu, are globular, and so if you want, you can consider them as being retrocells, but going in the opposite direction. Okay, so now I have this mu, which still goes from this to this, but it's a retrocell. I should have put identities here in identity morphisms with arrows. The identity is going from A to A, okay, from A to A, from left to right, and the same thing here. So in internal categories now are comonads in span ret, okay, so which is surprising. So when David a couple of weeks ago was speaking about category objects being comonads of polynomials, I thought, oh, that's weird. Why should categories be comonads? Well, they are in a ret. Okay, so now I'm happy with that. Yes, let's see. What is this here? But yeah, the whole point is that although the structure are globular, the morphisms are not, and so now in span ret you get cofunctors. Okay, so you're just looking now at morphisms of monads in span ret. So this is where the other kind of morphism of monads that you see in Street occurs. They're retrocells. Okay, so this is that, and you also get two cells, which I'm sort of rushing for time here. So I'll just do this quickly. You get two cells, and these give you, this is a very complicated thing, but it gives you the two cells for cofunctors, which the two cells for cofunctors are really weird thing. Cofunctors are weird, and two cells are twice as weird, okay? So, and it gives you the right thing here, which I don't have time to go into, but because I want to, so I also ran out of time, you know, with getting things teched, so I used, I photographed this. So I just want to say, okay, in the last 3 minutes here, double categories are good for combining kinds of morphisms that look like they don't compose, okay? And so here we have cells and retrocells, and the retrocells sort of go a little bit backwards and a bit forwards. And so you can make a double category of cells and retrocells. Okay, so the objects are vertical arrows, and the horizontal arrows are cells, but the vertical arrows are retrocells. And a double cell is a commutative cube like this. But commutative actually works in this case. The top is commutative because these are just morphisms, and the bottom is commutative. But now the theta and alpha and C and beta, they do compose, but they compose not in the same way as the top and the bottom. So they compose like this. This is a canonical cell here and here. Okay, so this is the double category of cells and retrocells. Now, since cofunctors were morphisms in retrocells, then we can bump this up to getting a double category of functors and cofunctors. Okay, and so just quickly here, these are categories A, B, C, and D. F and G are functors. K and L are cofunctors, so they have these lifting properties here. And a cell, alpha here, well, there's one, at most one, and there's one precisely when, first of all, the F and L and K and G commute on objects, okay? And secondly, we have the following lifting. So you can take an object A and a morphism in C, and you can lift it using K. Then you can apply F to it, and you get this guy, the top guy. Or you can apply G to it. Now this goes from GKA into GC. GKA is LFA, so they're equal. So now you have something from L of something into something. So you can lift that to F of A, and there will be a cell there precisely if for every A and C, this guy here is equal to this. So this is equal to this, and this is equal to this. So this gives you a nice double category of functors and cofunctors. But for the last minute here, I just have a dream that you can actually generalize this and get a much better double category of functors and cofunctors. So what I would like is that if K and L were identities, then this should be a natural transformation from F to G. And it's not in this case here because you see they're equal on objects. And if F and G are identities, it should be a morphism of cofunctors, a co-transformation. And well, I don't know if they are or not. Well, I don't think they are, okay. And so here is my last slide here. So whether this is better or not, I haven't checked anything of this and I don't know. But if you look, when the lifting down here had LFA equals GKA. So why not just put an arrow there? We can compose it. So instead of having LFA equal GKA, I put an arrow that's part of the structure. And then I can take the C, lift it, apply F or apply G, now compose with alpha and then lift this composite. And now I want to put another thing here. So I don't really know if this comes out of the theory or if I have to put it in a structure or what. I mean, so this is the fact that the slides here are paper rather than electrons, okay, is reflects the fact that I don't really know anyways whether this goes or not. But I believe that there is such a thing. I don't know what it's good for, but I think it's also good for something. And I'll stop there. Thanks.
Well, thanks a lot. That's a very interesting talk.
Thank you.
And I think we're going to have some questions here. Does
Sure.
anybody have a question for now? Please feel free to write in the chat or raise your hand. So in the, yeah, see, David Myers, do you have a question?
Yes. Well, this was really wonderful. Thank you.
Thank you.
Really enjoyed this talk and the notion of retrocell. So there's a construction that constructs, say, a new double category of not just of whose objects are the vertical monads and whose morphisms are the functors, but which also has bimodules and of monads and morphisms of those. So it constructs prof out of span, for example.
Yes.
If you do that if you take ret first and then you do the variant of that would be for comonads,
Yes.
You get another double category of cofunctors and of cofunctors and bicomodules.
Yes.
And now you have a way of having squares between functors and cofunctors. It seems to me that if you had squares between bimodules and co-bimodules, you could have some kind of cube. Do you have any sense of how?
Right. Well, I only sort of understand what you're saying, sort of 75%, but it does sound right to me. Okay, that you could do something like that. Okay, and it looks interesting to me actually that you could do this. I must say that I didn't look that much at this construction of getting the bimodules out of the original thing. Partly because you can't compose them in general, and so then you have to go to virtual double categories, and somehow I had some reticence about that. But I mean, I think that this is an important construction. Yes. Yeah.
Thank you.
Nice. Any more questions? So in the meantime, I have one, actually a couple. So one is, so you mentioned when you said that you talked about David Spivak talk about internal categories as comonads. That's analogous to what you find here. So is that just a coincidence, or is there some structural, more like deeper link between these two facts?
Well, I don't think there are any coincidences. Okay, I mean, there is a deeper link, and I'm not quite sure what it is, but it is interesting that that you're getting the same kind of structures, coming from two apparently different directions, and so there must be a reason for it, but not completely clear what it is, and you need to do some more work on that.
Nice.
Does that answer your question?
Yes.
Yeah.
And another one.
Yes.
So maybe to anyone that may answer, I don't know. Are there already double categories of functors and cofunctors arising, for example, from studying lenses or similar objects? I wish Bryce Clark was in,
Yes.
let's say, in our time zone.
He's probably asleep now.
Yeah, exactly.
But so yes, I think that lenses. I'm not quite sure, but if you look at this double category here, I think that lenses in this setting here correspond to conjoints. Okay, so that you have I think, I mean, I haven't worked it out, okay, because well, question of time, but I think that this here would be a functor, this would be a cofunctor. Well, but now they're being conjoints, okay, would say somehow that they're related somehow. So I think that these delta lenses are conjoints in this double category, but certainly I'd have to work that out, or maybe Bryce would. Yes.
Oh, interesting. Nice. Thank you.
Okay.
Okay. Does anybody else have any questions or any comment?
Looks like there are hands that are up there.
So, hands up. I
Yes.
don't see them.
Yeah, David's hand is up.
Oh, for some reason I cannot see the hands. Okay. Which David? David Spivak or David Myers?
David Myers.
Okay, please, David, unmute yourself if you have
All right.
another question.
Thanks. So I was just wondering if you knew what retrocells in prof were.
No, I don't. It's something definitely to work out. I mean, it was already sort of a bit involved just doing it for span. You know, so it must be something similar, but okay. So monads in prof are like Kleisli categories. Okay, so I think that it's a category and then another category, identity on objects functor between them. Okay, so, but yeah, it's something that should be worked out. You're right. Yes. There was one other tentative hand by the guy whose name I don't know, with the green shirt there. Yeah.
Green shirt.
Well, okay.
Who is that? For some reason, I cannot see raised hands. Apologies.
No. Okay. Well,
who has a green shirt other than you?
It wasn't me.
Okay, let me. Let's. Everybody's now free to unmute themselves. So if you have a question, you can. Was there a raised hand?
No. Okay. I thought I saw a raised hand.
Okay. So it seems that for now we don't have any more questions. So I feel we can move the discussion offline. So you can, in a moment, you'll still be free to ask questions, but they will not appear in the recording. So
okay.
Of course, for a moment, let's thank Robert again for the nice talk.
Thank you.